In this presentation, we're going to look at proof by induction. So what we're going to do is prove by induction this expression here. 1 plus 2 plus 3, all the plus n, is n times n plus 1 over 2. Just quick example of that. Let's just do this in black. 1 plus 2 plus 3 plus 4 plus 5. That's equal to 15. Okay. N there is equal to 5. Okay, so n times n plus 1 over 2, is 5 times 6 over 2. That's 30 over 2. That is equal to 30 over 2. You could tell now that is equal to 15. So this sort of checks out. But what we want to do is prove it by induction. The job here is to prove that by induction for all natural number values of n. Okay, so there's a couple of steps we have to do. First off, the base step. This is a very simple idea. When the n is equal to 1, show that n times n plus 1 over 2 is equal to 1. That's very straightforward. 1 times 1 plus 1 over 2 is equal to 1 times 2 times over 2, that's equal to 1. Okay, that's very straightforward. What you might do there in some cases is it might help to do the second one, n equals 2 as well. And those examples are a bit more complicated. You'll know them when you see them, actually. They're just when there's multiple phase recurrence relations and stuff like that. Now, the next step is the induction hypothesis. Assume that the formula is true for when n is some fixed but arbitrary natural number k. Sorry, that's a k there. Let's write it in again. So essentially what we're going to do is 1 plus 2 plus 3 all the way up to k is equal to k times k plus 1 over 2. This is what we call the induction hypothesis. This is, again, a very straightforward step. It's essentially just a sort of making this case, and what you do is create this induction hypothesis. Okay, so that's the key part of this. You create this induction hypothesis. Okay, there it is there. Now, the next step is the induction step. Now, this is the one we actually show the calculations. So, show that the induction hypothesis holds for the case where n equals k plus 1. Okay. So, previously we had the case where n equals k and just stated the induction hypothesis. Now that we have to show it for k plus 1. So, this is where the bit of maths comes in, a bit of guile comes in. So, here we have 1 plus 2 plus 3 all the way up to k plus 1. Let's put that in a little bracket there. Okay. And let's show that that is equal to... Let's sort of use our formula to sort of see what that would be equal to. Let's just sort of make the remark here. N is going to equal to k plus 1. N plus 1 is going to be equal to k plus 1 plus 1, which is equal to k plus 2. Okay, so we put them in there and there respectively, and then we divide by 2. Okay, so that is what according to our induction hypothesis, this is what we should get, or our hypothesis, this is what we should get. But what we have to do is just check, does it sort of stay consistent with our induction hypothesis? Okay, so what I'm going to do there is a sort of reflex action might be there to would be to evaluate that. But what I'm going to do is actually just rewrite it. These ones require a bit of guile, as I said before. So what we have there is k plus 1 times k plus 2 all over 2. Okay, now what I'm going to do is factorize that, or not factorize, I'm going to rewrite it as follows. K times k plus 1 plus 2 times k plus 1. What I'm going to do is rewrite it like that. Okay. And what I'm going to do now is split it up into two components. K over k plus 1 over 2 plus 2 over k plus 1 over 2. 2 times k plus 1 over 2. Okay, here the k plus 1's cancel out. Okay. So what we have here is this expression here. I'm just going to go to a new slide again. So what we have here is k times k plus 1 over 2 plus k plus 1. Okay. Now, according to our induction hypothesis, this here is equal to 1 plus 2 plus 3 all the way up to k. Okay. And if we add this here, that's adding k plus 1. Okay. So essentially, the induction hypothesis, the hypothesis holds for n equals k plus 1. N equals k plus 1. Does that work? Yeah, it does. It's consistent with the induction hypothesis. So that is it done. That's our exercise done. And do I have to sort of say anything here? No. Okay, that's it. Induction hypothesis.